A complement must be finite. Now, let me introduce notation AI. So I'm saying that AI is a collection of the points of x for which fi minus f is less than epsilon f. Then I can show that the intersection of such kind of AIs is an increasing sequence actually. Okay? And then if I take the union of such kind of increasing sequence, its measure would be equal to the limit n goes to infinity of the measure of the intersection actually. Now if this is true, then keep in view this. So imagine a point which is outside a complement, which is inside a or outside a, inside a complement. Then fn of x converges to f of x as n goes to infinity. Okay? Then what does this mean? This means that for a given epsilon positive, I can find always a capital N such that after that capital N, the difference of fn minus fx would be less than epsilon. In other words, that same x would be in, essentially one of these intersections actually. So it is going to eventually fall into one of the intersections. And why this is the case, think about it. Why intersection? Think about it. So if I'm saying that if x is in AI for n, then it must be in n plus 1 as well, and hence n plus 2, and hence n plus 3, and so on and so forth, and hence it belongs to that. Yeah. In other words, it's going to fall into this union. Okay? And therefore a complement is contained in this union. And I can say, I can say what? I can say that now consider this. The measure of x is bigger than or equal to this number, and hence it's also bigger than or equal to the limit. But this number, which is the measure of the union of the increasing sequence, is bigger than or equal to a complement, measure of a complement. Why? Because
a complement
just showed it. But the measure of a complement is the measure of x. So this means that the measure of x must be this number. And if this is the case, the measure of its complement must be 0. And if this is the case, what does this shows? That the measure of this union is 0. And now, what is eventually we want actually? So I have, a point, the collection of point fn of x minus f of x is bigger than epsilon, a set. So I'm going to say that this set is going to contain in this union actually. Why? Because, think about it, it contains all such basically such that it has all collection of points for which all such kind of expressions are true. So what does this show? That the limit of this guy would be less than or equal to the limit of the union of these basically. And since this is 0, so this limit would be 0 as well. Okay? And hence what does this show? That at least when your space is finite, your almost everywhere convergence is same as convergence in measure. And I also discussed this last time that the convergence, almost everywhere convergence can be replaced by almost surely convergence, and this also implies that almost surely convergence implies convergence in probability, which is just nothing, just replace convergence in almost everywhere. Convergence implies the convergence in measure. Okay? But obviously we need to think about that. Can we have an example in which I have a convergence in measure, okay, but it doesn't imply convergence almost everywhere. Okay? And the example that I'm going to use is going to be from probability theory. So take omega to be 0, 1. Take B to be the Borel sets, collection of Borel sets onto the 0, 1. Okay? And take so take the Lebesgue method. Okay? And consider a sequence xn of omega, which is the indicator function of 0 to 1 over n actually. Okay. I'll make a bit modification in it accordingly, but let me just say it out actually. So, okay. So what does this mean? If I want to explicitly write it, and since I have this Lebesgue measure, I can write that xn of omega is 1, okay, with the probability, okay, with probability of xn being the ये 1 कब होगा? If omega is in 0 to 1 over n, but what is meaning of omega being 0 to 1 over n? So it means that when the probability is 1 over n actually. So it's like the measure of 1 over n minus 0. So it's, and it's going to be 0 with the probability 1 minus 1 over n obviously. Okay. Does this converges in measure? In other words, consider the probability that xn goes beyond an epsilon actually. Okay? And for the sake of simplicity, I may assume that the epsilon is something between 0 and 1. I can make it arbitrary. I can make it arbitrary, okay? And say that epsilon is arbitrary, but it's a positive number. So this must be equal to what?
1 over n.
So this must be equal to the probability that xn is 1 over n. Okay? So xn is 1, sorry.
Yes.
Xn is 1 because if this is, okay, if x, like this is something positive, then it can't be 0. And when it is not going to be 0 when xn is 1 actually. And when xn is 1, so the probability of it is 1 over n. And then I can say that this probability goes to 0 as n goes to infinity. Okay? So we say that xn converges to 0 in probability. Xn converges to 0 in probability. Okay? How about, does it converges almost surely? In other words, almost everywhere? It can't be the case actually. Think about it. It can't be the case. Because no matter what epsilon you take and what n you take, okay, or I can say that there is a subsequence of xn which converges to 1, and there is a subsequence of xn which converges to 0. Okay? So if a sequence has two subsequences converging to different limits, that sequence cannot be convergent actually. Okay? So in other words, no matter what n you choose, and you can always find two indices, okay, that xn of omega is 1 and maybe xn of omega is 0, where m and m are indices after this capital N actually. So what does this do? This means that
It's in the
it's not convergent actually. So I can't say that xn is going to go to only 0. Okay? It is also going to go to 1 actually. So what happens? So what does this show is that xn does not converges almost sure. Okay? That can serve as a counterexample. That the convergence in measure does not imply almost sure convergence. Are we happy with this? Think about it. So if I have this sequence, okay, then if this can take any value, so it can take 1 and it can take 0, okay, for different kind of omegas. So no matter what we do, we can't force it to go to 0 actually. Okay? We can't force it to go to 0. So we can't avoid 1. 1 can pop up at any time actually. Okay, so there is a probability of happening of it. Just like there is a probability of happening of both actually. So you can't say that, xn goes to 0 or goes to 0. Okay?
सर मुझे इसमें मसला हो रहा है जो एक्सन ऑफ ओमेगा को आपने प्रोबेबिलिटी के टर्म्स में डिफाइन किया हुआ है P is equal to 1 over n.
What does this mean? So this will happen if omega is in this interval 0 to 1.
जी सर.
And what is the probability of happening of it?
सही है 1
So that's 1 over n.
अच्छा वो पूरा था ठीक है.
So I'm saying that xn of omega is 1. Okay, when omega is in 0 to 1 actually. So the question is, what is the probability of happening this? So that's 1 over n. Okay, so in other words I can say that xn of omega is 1 with the probability 1 over n and it's 0 with the probability. So it could be 0 and 1, anything. But you can't say that it will converge to 0 point-wise. Can't converge to 0. By point-wise I mean for every omega. So it's not necessary because it can switch between 0 and 1 actually. We can also see that convergence in measure also does not imply convergence, LP convergence actually. Okay. Convergence in measure does not imply LP convergence. Okay? We know that LP convergence implies convergence in measure, but not the other way around. What would be the counterexample? So see, so creating counterexamples here is pretty interesting and easy actually. But if I take this, so xn of omega is n with multiplied with the indicator function of 0 to 1 over n. Okay? Obviously operating on the omega. Alright? So what does this mean? If you want to write it probabilistically, so xn of omega is n with probability 1 over n, and it's 0 with probability 1 minus 1 over n. Okay? So if I say that what is the probability of xn being bigger than an epsilon? So this is same as probability is xn is n actually, by definition. So if it is not 0, then it has no other choice than taking the value n. But the probability of happening this is 1 over n. Okay? And this will go to 0 as n goes to infinity. Okay? So I can ask a question, does this converges in L1? Does it converges in LP? In general, the P is something between 1 to infinity. But let's begin with L1 actually. So for L1, I need to do what? I need to integrate it. Okay? I need to integrate what? Xn minus 0 over this interval 0 to 1 actually. But this would be 0 to 1 over n. Okay? And absolute of xn would be n and okay dp, probability measure or dm actually. Okay? But this would be what? This this is that you have n times 1 over n, okay, n times 1 over n the measure,
It's 1 or that.
so it's going to be 1 actually. Obviously this is not going to 0. So what does this shows is that convergence in measure also does not implies LP convergence actually. LP convergence. Are you getting the point? So these are the general results. So they are there. Okay, so it's like, so I know that in general that convergence in LP implies convergence in measure. In general, okay, I can use Chebyshev inequality. But in order to prove that this is true, I can take any sequence and any measure actually. And I can take any LP. Are you getting the point? So if this is just violated for one sequence and one measure, this is enough to show that, okay, this is not true. Are you getting the point? Okay. So I would suggest that, playing around with these coefficients, put n and n square and, putting different, coefficients in the front of indicator function would give you, allow you to create good counterexamples. Okay? So, think carefully about this example.